this next video, we're going to talk about the Jacobian matrix and 2D transformations of random variables. Remember in that last video when we were deriving the proof that the sample standard deviation appropriately standardized had a chi-square distribution, and I said put a pin in that for now. You probably don't remember where the pin was, but we're going to return to it nevertheless and talk about a simplified version of a result that I still find pretty amazing. So the result is stated as follows. Suppose that y1 and y2 are IID normal 0, 1 random variables and let y bar denote their sample mean. We're going to show that u, which is equal to y bar, right, and v, which is equal to the difference or the deviation between y2 and y bar, are actually independent random variables. The reason why I say this result is fairly amazing is because if we write out the formulas for u and v in terms of y1 and y2, so u is y1 over y2, y1 plus y2 over 2, and v is y2 minus y bar, which means it's 2y2 over 2 minus y1 plus y2 over 2, right? Which simplifies to y2 minus y1 over 2, right? It seems like there's no way these two things are independent. Look, u has y1 and y2, v has y2 and y1. Why should they be independent? But we're going to show they are. Now, the trick to doing this is to look at the joint PDF of u and v. And what we'd like to do is show that that joint PDF factors into a marginal for u times a marginal for v, right? If we can do that, that is by definition what we mean by probabilistic independence of random variables. In order to accomplish this, though, we're going to need a formula for this. And to get a formula for this, we're going to need to consider the question of what happens to the PDF of two random variables when you transform them, right? Because I know that the PDF for y1 and y2, since they're standard normals, right? I know that that PDF, and they're independent, right, is just going to be the product of their individual PDFs. Writing them out in excruciating detail just so you get used to writing those one more time. So what we need to know, right, and what we need to do is figure out, well, I have here two new random variables defined as functions of x and y. We'll call this one g1 and this one g2. And really, let's pretend here that I'm not being an idiot and that x is y1 and y is y2. And what we'd like to know is how does the joint PDF of two random variables transform under such scenarios? Okay. Now, so this is the generic situation we're going to be considering. Suppose that xy has a joint PDF f of xy of xy, and that we define two new random variables u and v in terms of those previous random variables x and y. We're going to have to use the inverse transformation as well, so we're actually going to do all this under this assumption that this inverse exists. And our goal is going to be to derive, actually not really derive here, but state a formula for the joint PDF of uv. To motivate what this formula is, I wanted to return to the more familiar 1D situation, which you've seen in the past. In the 1D situation, in fact, we saw an example of this in the last video. If x is a random variable with PDF fx of x and y equals g of x for some invertible function g, then the PDF of y is given by the following. All right. The first term here, all right, excuse me, not including that bar, is we just plug in, right? So if y is g of x, that means that x is g inverse of y, right? So we plug this in to the PDF of x, right? That's just a simple substitution. The next factor is a little more complicated. It's the derivative of the inverse of y. Right? If you want to derive this result, by the way, for yourself, I'll let you take a moment to try and do that. You start off by looking at the CDF and then use the chain rule to take its derivative, and you'll wind up with the formula we have right here. Okay. But I wanted to point out that this formula right here is actually intimately connected with the change of variables formula that you encounter in Calc 1 or Calc 2. Okay. So the change of variables formula for integrals says that if I'm performing an integral of f of x dx over some area A, and I want to make a u substitution, so u is g of x, meaning that the differential du is g prime of x dx, right? Then what would I have to do? Well, first of all, I have to figure out what this A region is now in terms of the random variable u. So that's just going to be g inverse of A. Then I would be plugging in x in terms of u, so f of g inverse of u. And then I would be multiplying here by the absolute value of 1 over g prime of g inverse of y. Right. Now, if you compare the two formulas, right, these terms match up perfectly once you note the sort of result from Calc 1 that the derivative of the inverse of a function is 1 over the derivative of that function itself. So, in order to get the PDFs for bivariate transformations of random variables, we just need to know what the change of variable formula is for double integrals. Now, if you haven't taken Calc 3 or seen this result before, I'm going to actually outsource some of that explanation to an excellent video by Grant Sanderson of 3 Blue 1 Brown, although this video was actually formed back when he was with Khan Academy. So please click on that link in the slides, or just Google Jacobian matrices by 3 Blue 1 Brown and it'll pop up. Now, the change of variables formula for double integrals, just wanted to make a couple explanations here. It looks very similar to the change of variables formula for single integrals, all right? Remember that we're using h as shorthand for sort of the inverse of g, right? And notice we have the original function with the substituted values of x and y. And then we have this term, absolute value of the determinant of j in uv, which is taking the place of that absolute value of the inverse derivative from the previous slide. Now, just for clarity, so this is kind of self-contained in terms of working with these formulas, what that Jacobian, that j of uv is, it's called the Jacobian matrix. Okay? What that is we take the derivatives of x with respect to u and v, and we take the derivatives of y with respect to u and v, and we arrange those into a 2x2 matrix, and then we compute the determinant by multiplying together the elements on the diagonal and then subtracting the product of the elements on the off diagonal. Right. And then just take absolute value of that result. Okay. So that means that this change of variables term here is exactly what we need to compute the PDF of a two-dimensional transformation of random variables. Right? With the change of variables formula in mind, we can return to the example that started off this video and look at the joint distribution of y, u, defined as the sample mean of two random variables, y1 and y2, and v defined as the deviation of one of those standard normals from that sample mean. We already established that we can rewrite u and v as simple linear combinations of y1 and y2 as follows. And I'll encourage you to follow along on scratch paper, but you can verify that if you subtract u from v based on these formulas, you'll get back y1. Whereas if you add u and v, you'll get back y2. Now, using this inverse transformation, we can calculate the Jacobian matrix containing all the appropriate partial derivatives. So the first row we have dy1 du and dy1 dv. And the second row we have dy2 du dy2 dv. And again, I really encourage you to check out that 3 Blue 1 Brown video to get some motivation about where all these different partial derivatives are coming from. In our case, with this being a fairly simple linear transformation, the partial derivatives of y1 are 1 and negative 1, and the partial derivatives of y2 are both 1. So the determinant of this matrix is just going to be 1 times 1, that's the product of the diagonal terms, minus 1 times -1, which is the product of the off diagonals, and that just simplifies to 2. So on the first slide, we wrote out the joint PDF of y1 and y2 by multiplying those two independent standard normal PDFs, and I'll encourage you again to go back and review that if this formula doesn't make sense. And at that point, it's just plug and chug, right? The first h1 of y1 and y2, that's the first component of the inverse transformation. That was just u minus v. The second component is u plus v. So plugging all this into the joint density of y1 and y2, we get a 1 over 2 pi e. I'm going to pull out that 1/2 u minus v squared plus u plus v squared, and then times that Jacobian. So we can simplify this a little. 2's cancel. Right? So we get 1 over pi out front. And then in the numerator, we end up with u squared minus 2uv plus v squared by expanding out the first square. And then u squared plus 2uv plus v squared by expanding out the second. Now again, these cross terms cancel. And then I'll note that we can factor the resulting PDF. I want to pull apart this pi for a moment for reasons which will hopefully become clear. We'll get a negative u squared, and then a second term which only involves the v squared, right? Because I can factor the joint PDF as a product of two individual density functions, one which involves u and one which involves v, we can conclude from this that the random variables u and v are indeed independent. Furthermore, and I'll leave you to kind of verify, you can actually show that both of these are normal PDFs, both with mean 0, right? And both with a standard deviation of 1 over square root of 2. Now, that's pretty amazing if you think about it. So not only are they independent, but they're independent with normal distributions. And that actually is an illustration of a more general result, which says that if you take any linear combination of normal random variables, then the result is also going to be normal with a covariance matrix that can be calculated with a different formula, but that's a video for another time. And now we'll stop here, and in the next video, we'll apply that change of variables formula in the Jacobian to computing the distribution of the ratio of two random variables, and finally get that t, that pesky t distribution to fall out of it. See you next time.